In this video, I'm going to show the image of why we need a fixed long loop PL in communication system. In wireless communication, the signals must be modulated and demodulated onto an appropriate carrier. As you can see in the frequency domain, the signal or information has its own bandwidth around the DC. At the transmitter, the signals must be upconverted to the frequency F1 from the baseband signal. On the other hand, at a receiver, the signals must be downconverted to the frequency around DC, which is the baseband signal S1. For the transmitter circuit image, the baseband signal S1 of t would be modulated or upconverted with the carrier frequency F1 through the PL's output clock source. Then, the upconverted signal would be passed through the bandpass filter and amplified by the power amplifier. Finally, the modulated signal is sent through the antenna. On the other hand, in the receiver circuit image, the modulated weak signal was received through the antenna and filtered by the bandpass filter and then was amplified by a low-noise amplifier. Lastly, the greater signal-to-noise ratio SNR signal was downconverted with the carrier frequency F1 through the PL's output clock source to a baseband signal S1 of t. Therefore, a PL is a must to provide a stable and adjustable carrier for both TX and RX in wireless communication. For the wireline interface communication, the digital PL data is sent by the TX, and then the RX receives the data. To make sure the RX output digital PL data is the same as the TX input digital PL data, both sampling clock frequencies must be stable and close. For example, if either frequency is moving around or unstable, both TX and RX data won't be the same. Similarly, if both frequency is different, both data won't be the same either. Therefore, a PL is a must to provide a stable and adjustable clock rate in a wireline interface. As you may know, the digital signal is more reliable than the analog signal due to several reasons. However, all your images are analog since we live in an analog world. What can we do? Yes, a data converter is a must to convert the data format between digital and analog. For example, a digital to analog converter DAC is to convert the digital signal D-in to an analog quantity like the output voltage Vout. The DAC converting rate must be stable. Otherwise, the output Vout would be distorted and don't present the D-in precisely. On the other hand, the ADC sampling rate must be fixed as well. Otherwise, the sampled V-in may even produce the wrong D-out digital information. Again, a PL is a must to provide a stable and adjustable clock rate in the DAC or ADC interface. Lastly, in the digital system, lots of digital elements like CPU, GPU, processor, memory, and digital logic gates, etc. must exchange data or perform data processing. If there is no timing information in an asynchronous mechanism, the communication inside the digital world will be messy and out of control. Therefore, a PL is a must to provide a stable and adjustable clock rate in the digital synchronous system to provide robust digital data processing. After knowing why the PL is a must, what are the requirements of the PL? Yes, the most obvious requirement is the frequency stability. In other words, the frequency must be fixed without moving. The constant frequency during the operation will make all systems predictable and reliable. What else could be the concern? Yes, noise. The circuit may have the noise inevitably, and those phase noise or jitter will still break the system operations. Let's take the jitter image as a case study and see how the PL's jitter would have an impact on the serialization operation. First, assume the clock-to-Q delay of the flip-flop is 0 for simplicity. Then, the output data D-out's transition time will align with a clock CK's rising edge in the ideal phase position. If the clock phase is not static all the time, the clock phase would be sometimes earlier or sometimes later than the ideal phase. Then, we call this phase uncertainty jitter. Obviously, the clock's jitter will directly translate to the output data's jitter. If the transmitter's output jitter moves too fast to be tracked by the receiver, the RX sampling point will be at the transition and get a high bit error rate. So, the fundamental requirement of the PL is the low jitter to reduce the bit error rate. But how do we get the frequency stability and low jitter at the same time in the PL? Think about your image for 5 seconds. Bingo! The negative feedback loop is the key. If there's a good reference and a negative feedback loop, the output Y will be close to the input reference as shown here. For example, if the output Y is less than the input ref, and the delta X will push the output Y to be bigger and close to ref. In the opposite direction, if the output Y is larger than the ref, and the delta X will push the output Y to be smaller and close to ref as well. To make the negative feedback correction clear, we can look at a simple voltage amplifier image as a case study. If the precise or fixed and no-noise voltage reference is available, then the Vref would be a reference voltage here. As you can see, if the output voltage Vout is greater than the Vref, then the delta V would be negative and drive the amplifier's output Vout to be smaller. Again, if the output voltage Vout is smaller than the Vref, then the delta V would be positive and drive the Vout to be larger. Therefore, Vout would be eventually the same as the Vref, and the delta V would be 0 in the steady state. After understanding the voltage quantity in the voltage amplifier, a similar phase quantity correction will be applied at the phase loop. In a real application, the crystal oscillator is the reference clock to provide a constant frequency and low phase noise or jitter for a PL. Then the PL's output clock phi out will produce a constant frequency with the low jitter as the input. However, there is a subtle limitation of the crystal oscillator is that its frequency is constant without any adjustment. Furthermore, the frequency is quite low, around tens of megahertz range, even though the phase noise is quite low. Due to those two constraints, the PL might not be applicable. What can we do? Think about your own images for 5 seconds. Yes, frequency divider or multiplier can enhance the PL's frequency synthesis ability, such that it can be applied to all kinds of systems. In this example, putting the frequency divider at the feedback path such that the output frequency of the divider will be the same as the reference frequency. So, the output frequency is equal to the n times reference frequency. Simply by adjusting the number of n, all kinds of output frequencies can be synthesized if the PL's voltage control oscillator can produce these frequencies. Here is the summarized image you may have for a cell phone or wireless and wireline system. No matter the Wi-Fi, cellular, Bluetooth, etc. wireless system, or the PCIe, DisplayPort, USB, CPU, GPU, memory, etc. wireline system, the clock or the PL is a must for each communication system. Therefore, the cell phone may need multiple PLs to support different frequencies and the jitter or phase noise requirements, which could be fine, but the crystal oscillator would add more cost and bulky to the system. So, it's preferable to have a single crystal oscillator and distribute it to multiple PLs as the reference clock. Lastly, This image should give you an intuitive idea of why the PL is a must in communication. Thanks for watching. Before you go, if you are benefiting from those 30 images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may benefit from it.